iterative. DFS. And
UCS.
UCS. All of them without estimation of goal. Yeah, that's one. The second one is informed search. Yeah, informed search. We divide informed search to two parts. Yeah. Again, UCS. And S. That's okay. That's okay. No, go. Last one, show me. Your group is ASA is a combination of uniform cost search and good estimation of goal or distance to goal. In the last week, we discussed on the different implementation of such ASR. BFS, DFS, uniform class. It is an implementation of the grid research, similar to UCS. Yeah. And the solution is not optimal because it is greedy algorithm. If you use uniform cost search, you cannot guarantee to find optimal solution for the informed search. Yeah, for informed search. But when we add the heuristic, the condition is better. For defining the heuristic, good estimation is needed, not just estimation. Because of that, for example, as you remember, this heuristic is useful and we can find the optimal solution with respect to this heuristic. But for another example, this one, heuristic is not good because we estimate the path between S and G with a great value. 7. 7 is very, very great. Very greater than the exact cost. The exact cost between S and G is 4. But this is not good. Because of that, we say that instead of good, admissible or optimistic heuristic. But what is the definition of the admissible heuristic? We say that in mathematics, if H for any node, heuristic for any node, be positive or 0 and less than exact cost, we refer to such edge as admissible heuristic. Yeah? We say that edge is admissible heuristic. But for finding edge, we need to the value of H star. star is exact cost or optimal cost. But we have not any information about the optimal. If you access to the optimal solution, the problem terminates. Because of that, for defining here admissible heuristic, we follow instead of solving this problem, we ignore from some concept. Consider this one. We should minimize an objective function z equal to fx, x vectoral variable, x is a function, z is the value of f with respect to x, subject to. What's our constraint? Some of the constraints are inequality and some of them are equality. We say that g I x less than or equal to bi for I from 1 to n, and h j x equal to 0 for j from 1 to n. This is the original problem. Now, step 1. Step 2. In the heuristic, because I need to define some estimation, we can ignore from some of the constraints. For example, I can ignore from a single constraint from the inequalities or equalities, or a band of the inequality or equality. In step 2, ignore from at least some constraint. If you ignore from some constraint to define a simpler problem, a simpler problem, a simpler problem to solve. Step 3. When you ignore from some constraint, you can find a new algorithm for solving the simpler problem based on the solution of simpler problem, you can estimate the here admissible heuristic for the original problem. Example. Consider a problem to minimize minus x minus 2y. Subject. X plus y less than 2. X two plus y 2 equal to 1. X and y positive. Of x positive, y positive. I draw the feasible set. In Cartesian, x and y. The first one say that x plus y less than 2. I choose 2 and connect these nodes together. I need less than 1. X plus y less than 2. This is the constraint 1.
1.
Now, for the second, x2 plus y2 equal to 1.
واحد تربيع زائد واحد صح واحد مضمون.
This is a circle. And you should x2 plus y2 equal to 1. Just the trapezoid circle. And x, this is 2. And x greater than 0 and y greater than 0. You should solve this problem on the intersection for all of the constraints. The intersection for all of the constraints is this green part located on the circle, less than constraint 1 and greater than 0 based on the constraint 3 or 4. Now, return to problem. The original problem has an objective function. Yes, I have an objective function. Some constraint as an inequality. I have some inequality. And equality constraint. I have equality constraint. In a step 2, ignore from at least some constraint. For step 2, I ignore from constraint 2. Ignore constraint
2.
2. The problem is simple. The feasible set contains such nodes. I return to the objective function. I need to minimize x and minus 2y. If I set with non-zero x and 0y with greedy algorithm, I can receive to this, I can receive to this point x equal to 2. With respect to this solution, the objective function is minus 2. Yeah? Again, I set x 0 and permit to get positive value for the y. Y can add it to 2. Yeah? Y equal to 2. By substituting y equal to
1.
and x is 0, z is minus 4.
4.
Minus 4 is better than minus 2. Because of that, the solution x and y equal to 0 and 2 is optimal for simpler problem. Z star is equal to minus 4 is a admissible heuristic for original problem. Because minus 4 is less than the optimal solution of the original problem. The optimal solution of the original problem is minus 1.
Yes.
It is h star x. But instead of solving a nonlinear problem, I simplified it to a simpler one by ignoring from this nonlinear constraint. I ignore from this nonlinear constraint, transform the original problem to a linear problem, solve it, find the optimal solution and the optimal value. With respect to optimal value, I find a heuristic for h star x. Example 2. In this example, I need to, I wish to travel from origin S to target T. This is my graph. S, for example, this is source and this is target. For any I and J, I define Cij as the cost. Now, I wish to travel from origin S to target T in the travel time less than a given time t. This problem is very complex because I should define a shortest path from S to T by minimizing Cij, but any link has a time Tij as the traverse time. Similar to this one, I can implement a mathematical problem for solving this problem. I say that I need to minimize a cost Z equal to the past cost. The past cost is summation of Cij as the cost of any link cross Xij when I and J belong to set of links A set of links. What's the meaning of Xij? Xij is a binary variable equal to 0 if I and J is not shared in paths. Ij is not belong to paths. And one otherwise. If you calculate Cij multiplied in Xij, some of the links are not selected, they are 0 and they cannot increase Z. Some of the links in the, for example, shortest path, maybe it is shortest path, maybe the link of S to 2 is 1 multiplied in corresponding cost plus 2 from 4. X to 4 is 1. The corresponding cost is multiplied in. Again, for all of the links sharing in the paths, you can calculate the cost. And for constant, subject to. x, I, j for all of the j when I and j belong to A minus x, j, I for all of the j where j and I belong to A equal to assume regarding the S, I should select one of the neighbor of S for travel. Maybe 1 or 2 or 3 is selected. One of them. This summation count the links that selected as the output of I, because I consider the link I to other J's. Because I select one of the links, this summation is 1. But the second summation is the summation of the links who are enter in I. But I is source. We have not come back to source. Because of that, the second summation is 0. 1 plus 0 is 1. When I equal to source or origin. For the target, we have not exit from target. Because of that, the first summation that count the edges that are used for exiting from the node is 0. All of them are 0. But from one of the neighbor, I enter to target. Because of that, the second summation is 1. And we have a minus before the summation. 0 minus the summation is minus 1 for I equal to t. For I different from S and T, for example, this node. Once we enter to I and once we exit from I. The first summation is 1 and the second summation is 1. 1 minus 1 is 0. Or maybe I don't choose this node. When I don't choose this node for travel, the entrance to the node is 0. The exit from this node is 0. 0 minus 0, again 0. This is the concept similar to this one. And for the last, travel time less than theta. To implement this constraint, I write another summation, multiply Tij in Xij for all of the Ij belong to A. If you don't choose Xij, it is 0, and the summation doesn't change. If you use Ij for travel, the corresponding travel time is added to your travel time. Because of that, this summation counts your travel time. It should be less than theta. This is our discussion. Now, come back to our algorithm. Step 1, it is necessary to represent the problem. We represent the problem as a mathematical model. Number 2, ignore from at least some constraints. If I ignore from some constraint, I can select one set of the constraint I have a great number of constraints. I can ignore from this binary constraint. And instead of binary constraint, I can assume that Xij is real and the corresponding problem is linear programming. Step 2. Heuristic 1. Ignore red is constraint. Blue or to start. This is one star and this is choice. Yeah. First heuristic, ignore from 3 star. The problem is this is linear function. Again, this is linear function, and the last one is linear function. By ignoring from constraint 3 star, the problem is simplified into a linear programming problem that can be solved by simple example. As you remember in step 2, where we ignore from at least some constraint, the simpler problem is defined based on the solution of the simple problem. We can estimate the admissible heuristic. In this case, by using simplest algorithm, we can solve that problem, and based on the solution of the simplest algorithm, we can estimate an admissible heuristic, heuristic 1. Heuristic 2. Ignore from 2 star. Ignore from to a star. If you ignore from this constraint, this objective function should be minimized with respect to this constraint. It is similar to knapsack problem, because in knapsack problem, in the theory of algorithm, you try to find the best items to insert in your knapsack with respect to their cost or weight, and each of the item corresponded to a needed capacity, and because of the exact capacity of the knapsack, you should select the best items. Here is to ignore from to start. The problem is simplified into knapsack problem that can be solved by grid algorithm. Again, a simplified problem is obtained. You can solve an abstract problem with different algorithms, such as grid algorithm. You can find the optimal solution or near optimal solution, and the obtained solution is an admissible heuristic for the original problem. Heuristic 3. You can ignore from this constraint. Ignore from one star. Yeah? The problem is simplified. Without this constraint, you just need to minimize this objective function with respect to shortest path constraint. Because of that, the problem is simplified to shortest path problem that can be solved by Ldektor algorithm or AS. Again, with respect to the solution of Ldektor algorithm, you can define an estimation, an optimistic estimation of heuristic, and again you can solve this. This example shows that definition of the heuristic is not unique. We can ignore from different constraints and simplify our original problem into different models. All of these simplified problems are solvable with different algorithms. The first one can be solved by simplex algorithm. Are you familiar with simplex algorithm? No one? In the theory of algorithm, we have a good algorithm for solving all of the linear programming problems. One of the best algorithms is simplex algorithm. Also, there is iter-point algorithm for solving this problem. Not important because there are a lot of software that can solve linear programming. This is the first heuristic. The second heuristic is knapsack problem. Are you familiar with knapsack problem? Yeah. By different algorithm for knapsack problem, it is possible to extract the estimation of the original problem. This is a good way to implement heuristic. And for the last one, by considering the by ignoring from the red constraint, it's possible to define a simple model with respect to finding the shortest path. It is solved with die-cluster. Are you familiar with die-cluster algorithm? Die-cluster is similar to ASR. Similar to ASR. Again, we can solve it, and by solving this problem, it is possible to define a heuristic for the original problem. Simple example of the heuristic. As you see, again, the original problem has different constraints for moving around the cell, but when you consider a simpler problem without the exact constraint, you can fly from the origin to destination. Because of that, you can define a heuristic, completely adaptable with my algorithm. And for the second one, you ignore from the constraint of the barrier. Again, you can define a straight line for your movement, and based on this simplified problem, you can define a heuristic. And this is the definition of the problem. We prove that the ASR can find the optimal solution at the least time. This means that the optimal solution can be solved before any suboptimal solution. This is good idea. Please remember this important phrase in your mind. The relax problem. Relax problem is similar to this simpler problem. In our book, we refer to simpler problem as the relax problem. Relax problem is a problem where some of the constraints are relaxed. When ignore from some constraint, you relax the corresponding constraint from consideration. It is the meaning of the relaxed problem. In the mathematical book, they say that log, run, Gian, relax, problem. All of the terms are equal. Singular problem, relaxed problem, Lagrangian relaxed problem. And based on the relaxed problem, it is possible to solve the original problem easily. Remember that we solved a puzzle problem in which the tilts can be relaxed and the constraint over them can be ignored from different heuristics. As you remember, we defined two different kinds of the heuristic. One of them count just the number of mislocated tilts. When you consider mislocated tilts as a heuristic, as you remember, the iteration number decreases from 112 to 30. That is very, very good. And from 6,300 to 39. That is very, very good. And when we change the heuristic to a more modern heuristic, and compare the new heuristic based on the Manhattan. Manhattan is very complex distance, but improves the number of iterations. As you compare, in the first row, we consider the mislocated tilts, just mislocated. We can't mislocated tilts. In the second, we enumerate the iterations to reshape the tilts. The second one decreases again the amount of iteration. Thus, for very hard problems such as example 2, by using different heuristics, you can receive two different problems whose iteration time for solution is very, very different, and you can compare them in some tables similar to this table. In each row, you can consider the different simplified problems. For example, now we have 3 simplified problems. We have 3 rows, and for the different steps, you can compare the number of iterations. It is not possible to analyze mathematically which of the heuristic is better. Just based on the experiments, we can compare them, and it is a good idea for extending the heuristic for real problem, and you can write modern papers with respect to such idea. No. We need to extend A star algorithm for graph search. As you remember, the base of heuristic is to, before clearing the blackboard, if you need to capture from the blackboard, you can capture it from the front. Because they are not included in the lectures. Maybe you need it for solving. Yeah? Yeah? That's okay? In the tree search, we define A star including G, N, H, N, and F, N, as the sum of Gn plus Hn. Gn is backward cast, that is exact. Hn is forward cast, and it is estimation. We check all of the nodes with respect to Fn. In the graph search, again we consider this ASL. But we say that here admissible heuristic is not enough for graph search. We need more modern heuristic for graph search. The algorithm is similar, but the admissible heuristic is not satisfied. To present the reason, please consider again the graph search and tree search. In the tree search, you can follow any node from root by a single path. For example, if you are interested to the path to I, you just select a single path from root to I. There is no other option. But in the graph, you face with loop. When you face with loop, for example this one, in this graph, from R to, for example, I, there is
loop.
these, because of the loop, you can define different paths. For example, this is a single path. This is another path.
Yes.
You can select this path.
Okay.
Because of that, just using admissible heuristic is not sufficient power to guarantee to find the optimal solution. For some graph, it is possible. For example, say, see this graph? As you see, in this graph, we have not any loop. Yeah? We have not any loop. And the heuristic is admissible. Now, for example, for G, the heuristic is 0. It is a good, it is a lower bound of the exact cost. For C, is it admissible? H is admissible for C. Yeah?
Yeah.
1 is less than 3. Again for B.
Yeah.
Yeah. 1 is less than 5. Because there is no loop in this graph. If you implement A star, see, we started from S, G is 0, H is 2, we select the neighbors. Neighbors is A and B. Both of them contain G equal 1. And the heuristics are different, 4 and 1. A value for B is better than A. Because of that, we select B for expanding. By expanding B, we go to C. C is 3 as G and 1 as the H. Again, 3 plus 1 is less than label of A. Thus, we continue from C. G is selected. G is 6 plus 1. Are you terminated? Are you terminated? No. There is a better option. A has the cost 1 plus 4. It is less than 6. Because of that, we should continue. By continuing this, no, we receive to C again. The G is 2 and the heuristic is 1. Again, we continue. G is obtained with the neo label 5 plus 0. Although the graph is given, but because there is no loop, the original ASR works good. But for the graph with loop, we should search similar to BFS. Yeah? BFS. BFS is a good idea for searching the graph, but we should say around a node memory.
Max.
Yeah, a memory for saving all of the nodes that are traversed by ourselves. For example, I am here in J. There are 2 neighbors, 1 or 3. One of them is chosen. For example, 3. I write in my memory 3 because in the next step I do not need to traverse to 3 again. I continue the search. After some steps, because of the loop, I return to 1 again. I remember that 3 is traversed. I don't choose 3 for the next expansion. Just I can select 1. Again, I write 1 in the memory. Continue. Because of the loop, maybe I return to 1. I remember that 3 and 1 are traversed. There is no other option. We come back. It is the meaning of closed set. Closed set is a memory including all of the nodes that you selected for expanding in the previous steps. When you select one node for expanding, you save it in the closed set. And when you need to select one of the nodes for the next expanding, you compare them with this set. If they are traversed before, you don't select them again, and come back. Important. Store the closed set as a set, not this. If not new, skip it. If 3 is not new, skip it. If 1 is not new, skip it. And by using searching algorithm by a closed set, you can solve every graph search efficiently. Every graph search efficiently. It is the important part for graph searching. And another solution. We extend the meaning of heuristic. As you see, there are many different ways to access to any node. If heuristic to any node, for example, n, is less than or equal to all paths cost from a state and to target state. In the admissible heuristic, we have just a single pass. Because of that, Hn always is less than itself. Yeah? Because we have a unique pass. But in the graph, all of the paths should be checked. Because of that, Hn should be defined as a lower bound for all of the paths. This means if I have an option for traverse from A to C, HA should be less than HC plus cos A to C. I have different neighbors. Based on the different neighbors, I should satisfy this constraint. I have a lot of paths from my state to the target. All of the paths should be calculated, and the lower bound of the cost should be selected as the Hn. But it is very, very hard to define for real problems. For admissible problem, I have a good algorithm with respect to relaxed problem to find admissible heuristics. But for the consistent heuristic, this is consistent heuristic. Consistent heuristic. Defining consistent heuristic needs to analyze all of the paths between the any node and the target. And this is very, very hard to implement because finding all of the paths is a complex problem in theory of graph. Because of that, although the graph search can be implemented by A star, but in the A star, instead of admissible heuristic, we need consistent heuristic for graph search. And finding the consistent heuristic is very, very hard. This is the meaning of heuristic, as you see. As you see, there is a path from A to G. The cost is 4. Because of that, H should be defined as the lower bound of the 4. The lower bound of the 4 is 4, 3, 2, 1, 0. But if you define the heuristic equal to 5, your heuristic is not admissible. It is not consistent. For this one, the heuristic for C is 1. The cost is 1. 1 plus 1 is 2. The heuristic is not consistent. Because the heuristic of A is 4.
4.
We should change 4 to 2. Yeah. It is the process of improving the consistent heuristic. You should check all of the different paths from the source, from any node to the target, and based on the different paths, you should define the lower bound. Based on the lower bound, you can define and modify the consistent heuristic. If you access to a consistent heuristic as I presented here, again the A star is optimal for graph searching. That means A star can find the optimal solution before any sub-optimal. But the concept is consistent heuristic. The admissible heuristic is just for the graph without the loop. For graph with loop, we need to satisfy consistent heuristic. As the summarization, with admissible heuristic, 3A star is optimal. Okay. With the consistent heuristic, graph A star is also optimal. Great. And before defining the heuristic or considering H equal to 0, A star transforms to uniform cost search. And again, by uniform cost search, we can find the optimal solution, but the iteration number is very, very great. As the last, I presented some quiz for yourself to check the definition of the different admissible heuristic or consistent heuristic that is necessary for different practical problems. In the first one, I consider some gameplay. In the second quiz, I consider scheduling or timetabling. Similar to this one. The scheduling or timetabling is similar to this problem. You can check them to extend your knowledge about definition of the heuristic. The second one is machine learning. Defining the heuristic for machine learning is very, very important. And also for natural language processing, it's possible to define the heuristic. And in the real situation, there is a different kind of heuristic for such problem. And for network design and optimization, it's possible to define the different heuristic as I explained about the relaxed problem. You can define some kind of the heuristic for such problems. And job scheduling and manufacturing, there are very different kinds of the heuristic. That's okay. We are familiar with two kinds of the search, informed search and uninformed search. But both of the algorithms for informed search and uninformed search contains a single agent. In the next section,
multi.
we increase the knowledge on multiple agents, and also in this problem we have an objective function and a set of constraints. Again, we can ignore from the objective function. By ignoring the objective function, we receive just some constraint that should be satisfied. This is the meaning of constraint satisfaction problem. Constraint satisfaction problem is similar to my example. By ignoring the objective function. For both of these extensions, in next lecture we discussion together, and we try to implement some algorithmic approach for solving them. Thank you very much. I'm ready for your question. If you have any ambiguity in some part, please ask me.
No one.
No problem?
No problem.
Thank you very much.